Hi, this is Shyamala Gauri, Assistant Professor in CSE Department, Rohini College of Engineering and Technology. Subject code CGS 355, Neural Networks and Deep Learning. Unit 3, Third Generation Neural Network. In this presentation, convolutional neural network, the convolutional operation, the pooling operation are presented. Convolutional neural network. The convolution operation is a fundamental process used in convolutional neural networks, which are a type of neural network particularly effective in processing data that has a grid-like structure such as images. Motivation. The motivation behind using convolutions is to extract local features from the input data, example images, by emphasizing patterns that are spatially close to each other. For example, in image processing, convolutions can help detect edges, textures, or other basic features in small regions of the image, which are then combined to recognize larger structures. The convolution operation. What it is? A convolution involves applying a filter, also called a kernel, to an input such as an image by sliding the filter over the input and computing a sum of element-wise products at each position. The result is a new feature map that highlights certain features in the image. How it works. Suppose the input is a 2D image and the filter is a small 2D matrix. The filter slides over the image and at each position the filter is multiplied element wise with the part of the image it is covering. The sum of these products is then stored as a single value in the output feature map. This process is repeated for all positions in the image, resulting in a feature map that represents the presence of specific features detected by the filter. The key points in convolution operation are local receptive field. Each filter looks at a small region of the input at a time, which makes convolutions good at detecting local patterns. Shared weights. The same filter is applied to the entire image, allowing the model to learn translation invariant features. That is, features that are detected no matter where they appear in the image. Multiple filters. By using multiple filters, the network can detect different features such as edges, textures, and corners. Motivation for convolution operation. Number one, capturing spatial hierarchies. Convolutions help networks learn spatial hierarchies starting from low-level features like edges and progressing to more complex patterns like textures and objects. Number two, parameter sharing. Instead of learning a different set of parameters for each part of the image, a convolutional filter is applied to all regions of the image. This significantly reduces the number of parameters, making the model more efficient. Translation invariance. Since the same filter is applied at different positions in the image, the network can recognize features regardless of where they appear in the input. This makes CNNs robust to translation changes in images. The pooling operation. Pooling is another important operation in CNN used to reduce the spatial dimensions of the input, typically after applying convolutions. Types. Number one, max pooling. In max pooling, for each region of the feature map, only the maximum value is retained while others are discarded. It retains the most prominent feature in each local region, which can be important for capturing significant patterns. Number two, average pooling. In average pooling, instead of taking the maximum value, the average of values within the pooling region is computed. This approach is often used when a more general representation of features is desired. Motivation for pooling. Number one, dimensionality reduction. Pooling reduces the size of the feature maps, which decreases the computational cost and the number of parameters in the network. Number two, translation invariance. By summarizing regions of the feature map, Pooling operations help the model become more invariant to slight translations or distortions of features in the input. Number three, control overfitting. Pooling provides a form of regularization by reducing the risk of overfitting through dimensionality reduction. Thank you.